Hello and welcome to the 11th session of the Introductory Biostatistics Distance Learning course. Today in this session we're going to try to combine a bit of lecture with the STATA lab, hopefully be able to do both in one session. You'll remember at the end of lecture 10 we were talking about ANOVA, analysis of variance, which is the analysis we use when we have a continuous outcome and a categorical predictor, such as different groups. And we were looking at an example of hypointensity as the continuous outcome, and the categorical predictor was healthy controls versus people with benign MS versus secondary progressive MS and primary progressive MS. So a categorical predictor which said which group different patients belong to. And we conducted the ANOVA test, and we wound up with a significant p-value, which is a p-value less than 0.05 for the null hypothesis that I have written here, that all the means are equal in the n different groups. In our example, we had 4 different groups, but ANOVA's general can handle up to n different groups. So once we get a significant global p-value, sometimes it's called, from the ANOVA test, all it tells us, remember that the alternative hypothesis here is that at least one mean is different. And so we rejected the null that they were all equal, but we didn't yet know which one was different from which. And that's why we want to now conduct pairwise comparisons, which is going to be the topic for the lecture portion of this session before we move to illustrating how to conduct ANOVA in STATA. Okay, so we're talking about pairwise comparisons once we've conducted the ANOVA, gotten a significant p-value, so we know at least one mean is different. Then how do we conduct those pairwise comparisons so we can figure out which mean is different from the rest, or there might be several means that are different from the rest. Okay? So now we could go to pairwise t-tests, which we learned previously, to calculate p-values for the pairwise comparisons. And then, remember, we had also talked about this issue of multiple comparisons. That's when you do lots of tests, you get an inflated type 1 error rate. And remember that a type 1 error is when you falsely reject the null. So the null is true, but you decide to reject it. That's a type 1 error. That's a bad decision, something we want to avoid. And we know that as we do more and more tests of null hypotheses, our type 1 error rate can get inflated. So as a result, we have to take into account multiple comparisons. Okay? And so as a bit of a review, remember that we talked about this thing called the family-wise alpha level. And so remember alpha, which is our type 1 error rate, we said if we have multiple tests, then in the example where we had 4 groups, our overall family-wise error rate was calculated in this way, 1 minus 0.05 to the 6th power, which turns out to be, if you carry out the calculation, it turns out to be 0.265. And so now this 0.265 is much larger than 0.05. So that means we're likely, if we're going to conduct 6 different tests, we're very likely to make a type 1 error rate, and so we want to avoid that. So what if instead of using the 0.05, which we normally use, we instead use an alpha of 0.05 divided by 6. So in that case, our calculation would look just the same, 1 minus, but now it would be 0.05 divided by 6, okay? So I'm just dividing by the number of tests that I'm conducting, and if we carry out this calculation, it's equal to 1 minus 0.951, which is 0.049, which is very close to the 0.05 that we want it to be close to. So you see what we did is we took our alpha level, 0.05, our standard alpha level, and then divided it by the number of tests that we're conducting, And then we were able to end up at a family-wise alpha level close to the 0.05, which we desire. Okay? So this is called the Bonferroni correction, after a guy named Bonferroni. Bonferroni correction. Okay? So what we do is, there are two approaches which are completely equivalent. So don't get them confused. They're doing exactly the same thing. But in one, we can divide the component-wise alpha level by the number of comparisons and compare to the adjusted alpha level. So what do we mean by that? So this alpha star, we might call it, is equal to our normal alpha, which is 0.05, divided by the number of tests. What can I call this? Maybe k. Okay? So in the example where we had 6 tests, we took 0.05 and divided it by 6, and that was our new alpha star. Okay? Completely equivalently, we could multiply the observed p-values, by the number of comparisons. So I've called that k, the number of comparisons. Whoops. By k, the number of comparisons. Okay? So, and then compare to 0.05. So hopefully you see why these two approaches are exactly the same. In this one approach, we take the 0.05 and divide by the number of tests. In the other approach, we just multiply the actual p-values by the number of tests and then compare it to the same 0.05. So if we got a p-value, as an example, here's an example. If we had a p-value of 0.03, 0.03, then we would need to multiply that by 6, and that would give us our adjusted p-value of 0.08 or 0.18, which is no longer significant when compared to 0.05. Okay, so that is what we call the Bonferroni correction for multiple comparisons. Okay, and we do this because when we're doing a large number of tests, we know that we're going to get inflated type 1 error rates, and we want to avoid that, so we do this thing called the Bonferroni correction. Okay? So what does this look like in STATA? Here is the result. So you can see here I've used this command called one way. Hypo is the outcome variable, the continuous outcome or dependent variable. Group is the categorical predictor or covariate, and then Bonferroni tells STATA that we want to do this Bonferroni test for multiple comparisons. Okay, so here you can see the p-value for ANOVA. This tells us that at least that we can reject the null hypothesis that all 4 means are equal. You can see the means here are summarized here. Their standard deviations are here. Here's the number in each group. That's very helpful information. And then here, that's our test of the global null hypothesis. And then at the very bottom are the pairwise group differences. These are pairwise group differences and Bonferroni corrected p-values. Okay, so you can see where you look at the column 0 and the row 1, so that means we're comparing group 0 and group 1, and their mean difference is this negative 0.01122 here. And then below that, this 0.34 is the Bonferroni corrected p-value, okay? So similarly here, if I go here, this is the comparison between group 1 and group 2. The mean difference is this thing, negative 0.00715, and the p-value is 1. Remember, p-values are probabilities, so these p-values are getting multiplied by 6, as we have 6 different comparisons, 1, 2, 3, 4, 5, 6. And so since p-values are probabilities and probabilities can exceed 1, it turns out that when you took whatever this p-value was alone and multiplied it by 6, it would be greater than 1, so STATA smartly just truncates it at 1 since we can't have probabilities greater than 1. And just as a final example, the comparison between group 2 and group 3, the mean difference is here, negative 0.0038, and again a p-value of 1, meaning that there's no significant difference. Here, however, the comparison of group 0 and group 3, you can see that there is a significant difference as evidenced by the Bonferroni corrected p-value of 0.004. Okay, good. And again, we'll go through an example in STATA ourselves, okay? So again, you'll recall the kind of duality or interplay between p-values and confidence intervals, okay? So you might wonder, what if I want to calculate a confidence interval for the mean differences using the Bonferroni correction as well? And what would that look like? So let me pull that up. It would look like this, okay? So just the form we had before, right? Here's the estimate, the mean differences, minus the t critical value times MSE here stands for the residual variance. Okay, so it's the same setup as before. Estimate minus critical value times some measure of the variance. This is the measure of the variance. And then on this side, we do the estimate plus the critical value times the variance. The thing you'll notice here is instead of our standard 1 minus alpha over 2, we now have 1 minus alpha star divided by 2, where alpha star is the Bonferroni corrected level. Okay? So same interplay between p-values and confidence intervals that we had before. Okay? So far we've said that we had 4 groups, which led to 6 comparisons. Right? So what if instead we weren't interested in all 6 comparisons of the 4 groups? And just to show you, remember there was group 0, 1, 2, and 3, 4 groups. And so the reason why we had 6 comparisons, we needed this comparison. 1 versus 1 isn't a comparison, obviously. This comparison, and then 2 and 1 we've already done. 2 and 2 isn't a comparison. 2 and 3, right? And then there's none of these left. Okay. Sorry, I messed that up. So if we have 0, 1, and 2, sorry, and 1, 2, and 3, that's why we had 6 comparisons, right? This one, this one, this one, and this, so on. Okay, so 1, 2, 3, 4, 5, 6 comparisons. Okay. Okay, so what if instead we weren't interested in all 6 comparisons, but instead we were only interested in comparing each of the MS groups to the healthy controls? Okay, how many comparisons would we then need to compare correct for? Well, there would be 3 comparisons, right? It would be healthy controls versus the benign MS, the secondary progressive MS, and the primary progressive MS. Okay, so in this case, we would then multiply each p-value by 3. Okay, so that would be, but again, these decisions need to be made before you look at the data. So if you decide before you look at the data, I'm interested in only comparing each MS group to the healthy controls, then you can proceed in this way. But, you know, otherwise you have all 6 comparisons to look at, and you'd have to multiply your p-values by 6. So there are other corrections besides the Bonferroni. The Bonferroni is known to be very conservative. By that we mean it's going to lead to large p-values. So you might be interested in other ones which give you a little bit more power to detect differences. So there's all sorts of other ones in STATA. There's one called the Tukey's. Pairwise comparisons. There's the Dunitz correction, there's the Chaffee, there's many others. Just know that Bonferroni is the most basic one and also the most conservative. So we can do others as well. Okay? So just to show you that STATA can pull off the others, here's the Tukey pairwise comparisons. That's the command TK comparison. It's the Tukey-Kramer pairwise comparison for the full name. And so you can see here are 6 comparisons. 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. And the asterisk here represents ones that are statistically significant. Okay. Okay. So let's think about some conclusions to this section. So we use ANOVA to compare more than 2 groups on a continuous outcome. That's a key point, that it's a continuous outcome variable that you have. And so the way we do this is by looking at the variability within groups versus the variability between groups. Okay? So if the variability between groups is more than the difference within a group, then the groups are likely not the same. Okay? And then once we do that, if pairwise comparisons can be completed if there's a significant difference between all the groups, but we have to correct for multiple comparisons. Okay? Okay, so, and again, just like any statistical procedure, ANOVA has certain assumptions. There are 3 main ones: that we have independent observations. That means that my hypointensity should not affect yours. There's only one measurement on me. So an example where we don't have independent observations is a longitudinal study where the same subject is repeatedly measured. Here we're just measuring people once, so that's why we feel confident that we have independent observations. Then we want to have equal variance in each group. And we said the word for this was homoskedasticity. And then we also want normality of observations within each group in the underlying population. Okay? And just as we said with the t-test, ANOVA is quite robust to departures from these assumptions, particularly the normality assumption, as the sample size increases. So as you get more than 30 or 50 sort of samples, you can feel confident that you can use ANOVA, okay? Okay. And again, the equal variances piece, this one, STATA provides this thing called the Bartlett's test of equal variance as part of its standard output, so you can assess that. And again, ANOVA is pretty robust to departures from this assumption of equal variances, but if it does not hold, we can pursue other options like an unequal variance t-test. Okay. And for the normality piece, we can do statistical tests for normality. One is called the Shapiro-Wilks test. And usually graphs are actually very helpful with this. So once you have a reasonable sample size, you can take a look at the graph and what that looks like. So here's a box plot of our 4 different groups: healthy controls, benign MS, secondary progressive, and primary progressive. Okay. And if normality doesn't hold, we have several options. One is, so if normality does not hold, then we can transform the data. And by that we mean we take our outcome variable, our continuous outcome variable, in this case hypointensity, and we can use a log transformation or a square root transformation, and these are helpful in transforming a skewed distribution and then making it look normal. So that's a helpful transformation to think about, the log transformation or the square root. But then you'll have to remember that all your results, if you proceed in this way, all your results should then be interpreted on the appropriate scale, whether it's the log scale or the square root scale and so on. Okay. And even if transforming the data doesn't work, then we can pursue non-parametric tests. So non-parametric means that you're no longer making parametric assumptions, and the parametric assumption of normality, right? So non-parametric tests are going to be discussed in a future lecture, but the equivalent of ANOVA, the non-parametric equivalent of ANOVA, is called the Kruskal-Wallis test. And again, we'll talk more about non-parametric tests in the future. Okay, we can also do a permutation test, which we'll talk about briefly. But again, these will all be discussed in a future lecture. Okay, so just a final word on where we are, kind of big picture. Always think in these terms, right? We have, we want to think about the type of outcome variable we have, the type of explanatory variables we have, and then once we know those two things, we know what type of analysis we can conduct. So today, and in the last session, we talked about a continuous outcome with a categorical explanatory variable, and we used ANOVA. We'll see in a future lecture that we can also use linear regression for this sort of setting, but for now we've talked about ANOVA. And as we work through the other sessions, we'll think about other types of outcome variables, be they ordinal or dichotomous, time to event, as well as other types of explanatory variables, continuous or dichotomous, and so on, and the corresponding statistical tests that go with those. Okay, so now let me transition to the STATA lab that corresponds with ANOVA. So we're just going to try to illustrate how to conduct ANOVA using our statistical software package called STATA. Okay, so you'll remember I'm using the SEPO dataset that we spoke about in the second session. So here we are in STATA, and we have the same 7 steps for hypothesis testing that we had before. So again, to use ANOVA, we have to think about a situation where we have a continuous outcome variable and a categorical predictor variable. Okay, so there wasn't anything that perfectly fit this structure within the SEPO dataset, so I'm admittedly kind of violating the rules a bit just so I can illustrate ANOVA for you using the SEPO dataset. So what I'm going to do is use the outcome variable here called death week, which is weeks on study at death. Okay, so so you should remember that this is a time to event variable, right? Weeks on study to death. But just for the purposes of illustration, I'm going to use this as if it were a continuous variable and not a time to event variable. Okay, and then I'm going to try to predict weeks on study at death with the variable called Rx only, which is the treatment arm that these different HIV-infected patients were assigned to. Okay, so the question I'm trying to investigate is whether treatment assignment in this randomized clinical trial affected time to weeks on study at death. Okay, and again, remember that this isn't exactly an appropriate test because this is a time to event variable, but I'm just making this exception for the purposes of illustration of ANOVA. Okay, so it's always good to start off with a bit of a summary so you know what's going on, and graphs are always helpful. So what I'm going to do here is just that, start off with a summary. And so the command I'm going to type in is by, by, Rx only. Remember, that's the variable that tells you which treatment arm different patients were randomized to. By Rx only, comma, and then space sort, colon, summarize, and then my outcome variable, which is death week. Okay, so you'll see I get these results here. If you look here, this is telling me here's the treatment, the patients who were randomized to this treatment. Nevirapine, ZDV 3TC is the antiretroviral regimen that they got. And here's their mean time to death in weeks, 142. And then here's the next treatment group, the efavirenz ZDV 3TC group. And here's their mean and standard deviation of time to death in weeks. Okay, so you can see they're pretty similar. 142 is the mean death weeks for the nevirapine ZDV 3TC group, and the mean time to death in weeks is 139 for the efavirenz ZDV 3TC group. And as you go down, it shows the results for all the different treatment arms. Nevirapine ZDV DDI group, the efavirenz ZDV DDI group, and so on. And then if I click here, there's actually more groups than could fit on one page. So you keep going and it shows you all the rest. Now I have all the groups. Okay, so it looks like we have 1, 2, 3, 4, 5, 6 different groups. 6 different treatment groups that were a part of this SEPO study, okay, that patients were randomized to. So if I look at the mean weeks, 142, 139, 126, 134, 140, 138, they all look pretty similar with the possible exception of this one, the 126, and that's from the nevirapine ZDV DDI group. So before I even conduct my ANOVA test, I have a suspicion that maybe that's the only one that's different from the rest, because the rest look pretty similar. 142, 139, 134, 140, and 138. Okay. All right. I can also look at a box plot by typing in graph box death week comma overlay Rx only. So again, that's graph box because it's a box plot, then my outcome variable death week comma over, and then Rx only, which is the groups that these different people fall into. And you can see it's actually not that helpful a graph here because this is a time to event variable, as we said. But again, we're kind of violating the rules a bit just for purposes of illustration. Okay. So how can we carry out such an ANOVA test? So we can do it in two ways. The first way, we can type in one way, and then the outcome variable, which is death week, one way death week, then the predictor variable, which is Rx only, and then comma tabulate. Okay? So again, it tells you the mean in all of the different groups, the standard deviation, and the number in each of these. And then down here is the analysis of variance table that we spoke about in lecture. And you can see that the overall p-value for the global test that all of the means are equal, is 0.0554. So again, remember that this 0.05 is not some magical cutoff. It's a probability, right? Probabilities are continuous. So this just means that this is very, very close to significant. You know, this is not any different than if we would have gotten a value of 0.049 here, for example. They're very similar. So for me, I would probably conclude that there's probably at least one mean which is different from the rest based on this 0.0554 global p-value that we got here. Okay, so keep that in mind. Nothing magical about 0.05. It's just a cutoff people have decided on, and p-values are probabilities. They're continuous, so any cutoff you choose will be arbitrary. Nothing magically different from 0.0554 from 0.049, for example. Okay. So since this is so close to the 0.05, I'm going to proceed with the pairwise comparisons because I want to know which group is different from the rest. Okay? So how do I do that? Well, I can type in the command one way death week, that's my outcome variable, Rx only, my group variable, comma, tabulate, just like we did before, but now I add this one last word called Bonferroni, which tells STATA that I want to do the pairwise comparisons, and since I know that I'll be getting into a multiple comparison sort of issue with inflated type 1 error rates, I want to adjust my p-values. Whoops, I spelled that wrong. I apologize. It's one way. One way death week Rx only, comma, tabulate Bonferroni. Okay. So we get the same results we got before up here, all the way down to here. And then this is the new part. So it's the comparison of weeks on study at death by treatment arm with the Bonferroni correction. Okay, this is like the output that we saw in lecture. So this tells me that there's on average a 3-week difference in death between the nevirapine ZDV group and the efavirenz ZDV group, and the number below, the 1.0, is the corresponding Bonferroni corrected p-value. Okay, so you can see a lot of these Bonferroni corrected p-values are 1, which says there's essentially no difference between these groups. The only one that's close to significant is just exactly the one we expected. The comparison of the first group and the third group, these values got cut off here, but if we go up, we can see that the first group is the nevirapine ZDV 3TC group, whereas the third group is the nevirapine ZDV DDI group. Okay, and so that's this group where they have a mean difference in weeks on study at death of 16 weeks, and that's marginally significant with a Bonferroni corrected p-value of 0.057. Okay, so you can see how that helps us interpret the results, and you can also see why multiple comparisons quickly just becomes a bigger and bigger problem. In class, we had an example where we had 4 different groups, and that led to 6 different pairwise comparisons. Here now we have 6 different groups, and you can see that there's 3, 6, 9, 10, 13, 15. There's 15 different comparisons here. Okay, so 6 groups leads to 15 pairwise comparisons, and you can imagine the family-wise error rate would be much larger than 0.05 if we forgot to use the Bonferroni correction. So you can see the number of comparisons quickly goes up as the number of groups that you're comparing goes up. Okay? All right. So again, just like we always do, we might you know, when we're first doing this, we wouldn't know the commands. Remember, we typed in one way and comma and tabulate and all this stuff. When we're first starting out, we wouldn't know those commands, so we can use the drop-down menus to do the same thing, okay? So how would we do that? We would go to Statistics, Linear Models and Related, ANOVA, MANOVA, and then choose one-way ANOVA, okay? When it says one-way ANOVA, we mean that there's only one predictor variable that we're interested in, namely which group patients belong to. In the example in lecture, it was the different MS groups. In this example here, it's the different treatment arms of an HIV randomized clinical trial. So in the future, we'll think about how several variables impact a outcome of interest, and that will be 2-way or 3-way ANOVA and so on. But for now, we're in the simple case of just being interested in one variable, which is group membership. So I choose one-way ANOVA, my response, and then I get this little menu that pops up. My response variable is death week, my factor variable is RX only, and then again, you can see there are different ways of adjusting for multiple comparisons. Bonferroni, Chaffee, SIDAC, and there's others. So I've checked the Bonferroni, and then when I hit OK, I get exactly the same results that I got by typing in the commands. Okay? All right. Good. Okay, so an alternative approach to perform a one-way ANOVA, instead of using the command one-way, we can also use this command called ANOVA. And so what would that look like? We just type in ANOVA, and then the outcome variable, which here we're using death weeks, and then the predictor variable, which is RX only. Okay, and you can see here's my ANOVA table as the result, and the p-value is here, 0.0554. That's the same p-value that we had above for the global test of all of the means being equal. Okay? So same p-value, just a different command for doing the same thing, same analysis. Okay? And again, if we didn't know the ANOVA command when we're first starting out, we could use the drop-down menus. We would go to Statistics, Linear Model and Related, ANOVA, MANOVA, and then Analysis of Variance and Covariance. So Statistics, Linear Models and Related, ANOVA/MANOVA, Analysis of Variance and Covariance. And once I click on that, and I get another one of these menus, my dependent variable is death week, my model, which is to say the predictors that I want for this outcome of death week, is RX only, and then I hit OK, And again, I get the same exact output that I got from typing in the commands. Okay? Okay, so now if I want to do pairwise comparisons, I can use this other command in STATA called test. Okay, so if I want to test whether the people assigned to the first sort of treatment are similar to people assigned to the second treatment. Actually, let me do the comparison of the first group and the third group, because remember, that's where we found the significant difference. So I would type in test. Test is this new command, 1.rxOnly. So rxOnly is my predictor. 1.rxOnly tells STATA, hey, the people assigned to the first treatment, and then equals, I want to compare to the third group, 3 times rxOnly. And here's that p-value, 0.038, okay? And so why is this different from what we saw above? Remember, above here, we had the Bonferroni correction. Our p-value was 0.057. Now I'm saying it's 0.0038. The only difference is this 0.0038 is not Bonferroni corrected, okay? So remember here we said we had 15 different comparisons, right? And so if I take 0.0038, my p-value from this comparison, multiply by 15, I get back 0.0057, which corresponds to what we got above. Okay? So be careful when you use this test command. It's not automatically adjusted for Bonferroni. It's not adjusted for multiple comparisons with the Bonferroni correction. It's just the straight p-value. And so in a lot of ways, this way is better with the Bonferroni command, because you know the p-values that you get back are already Bonferroni corrected. Okay? All right. Okay, so I will stop there. That's how you can conduct ANOVA using STATA. Again, remember that you actually need a continuous outcome variable. Here I've used a time to event variable, so I've violated the rules a bit, but I was just trying to find a way to illustrate ANOVA using the SEPO dataset. So that is all for now. So now we know how to do ANOVA, what it's about, the kind of a little bit of the background, and also how to conduct it using STATA. So I will stop there and see you in the next lecture.